today.
Okay, so that's probably close enough. It's going to take me some time to get this up here anyway. So, all right. So there was a question about one of the preparation assignments. Is that right?
Mm-hmm.
What was the assignment again while I'm pulling this up?
Lesson 5 preparation assignment, number 7, part F.
Okay, I'm just logging in here and it's taking its time. Why is this taking so long? Because I'm in a hurry, that's why. Oh, what's going on? My computer's being ridiculously slow right now. You can try to read it to me, but so a lot of times it helps to see. Let me refresh this to see if that helps.
So it says, what is the third quartile of the speeds of hydrogen at room temperature?
Okay.
After we already figured out.
Something's wrong with my computer. Okay, so it's probably got a graph there that I have to look at in order to see it. Is that right?
No, not a graph. Let me see if I can share my screen. Let's see. I think it's this one.
You just have to figure out the Z-score.
Okay, so here's number 7. Can you see that?
I'm not looking at my screen at the moment. Where'd my screen go? Oh, you're sharing it. I didn't know you could share it. That's kind of cool. Okay, that's even better. That's faster. Okay, so the mean speed of a hydrogen room is 1,800 meters per second with a standard deviation of 600. So part F, what is the third quartile of the speeds at room temperature? Okay, so I got it now.
Okay.
So do you have any idea how you would do such a thing?
Maybe by going into the probability app and.
Oh, that was a good idea. Very good. Okay, so do you want me to share my probability applet if it works? My computer's acting really goofy today. But yes, let's go.
We were having, so we were putting in the percentile in that probability app, but we weren't highlighting the right area.
Ah,
so
that can be a big problem.
If it's above 50, right, we have to highlight the right.
Okay, so.
Or maybe blue.
So you're saying, I don't know, what you said was not exactly accurate, okay?
Okay.
The idea here is you want, so in fact, it doesn't, honestly, let me highlight all 3. So it doesn't matter what you put here, what you highlighted here. If I want 75% here, and if I press enter, oh, sorry, never mind. I guess it does matter. 0.75. So I want the area to be 0.75, and then it will give me this area, the Z-score. So the area in blue highlighted is 75%. Okay. Now, just so you know, if I wanted the area to the right, I could do change it a little bit, but that's basically 75%. So that would tell me the area to the right would be greater than negative 0.674. Or if I want, in this case, it said it wanted the 75th or the third quartile, which is the 75th percentile. So I want 75% of my area, it won't change, to be less than, so your Z-score is 0.674. Does that make sense?
Yeah.
Okay, so you can use that for your problem there. So now you're going to plug that into the Z-score equation. This time you know your Z-score, which usually you don't know that, but this time we do. It's 0.674. equals x, which we don't know, minus mu, which was 1,800 meters per second, if I remember right, over your standard deviation, which was, I believe, 600. And then you just have to solve for x.
Okay.
So what if you're getting the 35th percentile?
So then you can change this. Now watch this. I don't think it'll matter what I've got highlighted here, but if I put in the 35th percentile, it knows that, oh, that's this side here. So it's going to be the negative 0.385.
Okay.
See, I got different answers. I got like a 0.454. And I don't know.
Was it, okay, so when I say negative 0.385, I'm talking about the z-score, not the answer to the problem. You need to take that negative 0.385 and then plug it into the problem, and that could be some other number.
If the middle, like, I think what I had was just the middle highlighted. Like if you just highlight.
Okay, so if you highlight the middle, that's going to give you a different answer.
Right.
That'll probably be the wrong answer. So the middle 35%, you'd use negative 0.454. But I don't know what the question is.
The z-score should be 0.385.
Right.
Okay, so that was the way I did it the first time. So if I shade the area to the left, and if I go 0.35, negative or 0.35, that gives me negative 0.385.
Okay. Right. So I was just doing that wrong, I think.
Yeah. Yeah, so you can click on this and you can do whatever you want, and whatever you click on, like if I wanted the middle area, I want that to be 30.35, it'll do that. I think that's the number you got. But if you want the 35th percentile, that means you want 35% to the left. And so that's going to change that. I hate that. 0.35.
Okay.
Which is negative 0.385. Does that make sense?
Mm-hmm.
Yes.
Yeah. So this applet, you are expected to be able to use on the test. So you need to make sure you know how to use that properly.
Okay.
Okay. So are we good there, Amy?
Yeah.
Okay. All right. What other questions do you have? Valerie left us. She was here before. What happened?
I don't know.
She's the one that answered all our questions, so
Oh.
maybe she thought she was good.
I hate this thing. All right. Text me a new code. Do you guys have to do this, or is this just teachers when you log
You
in?
don't have to do that.
Drives me crazy. But at least, well, I will say this. At least BYU, Idaho, you only have to do it every 30 days. At Utah Valley University, you have to do it every single day. It's so annoying. So she had a question about one of the quizzes, I thought, but I didn't hear what the question was.
Oh yeah, she had a question on one of the quizzes.
Different than our questions. We had the question, it was the same thing on that 35th percentile and the 80th percentile, but did she have another question?
Yeah, she had another question.
Oh, I didn't mean to run her away. All right, well, let's see here. So let me just look ahead to what we've got. So we're in week 3 right now, which is lessons 4 and 5. So we're going to do a little bit of then let's see, week 4.
All right, I have a meeting to go to. Thank you for your help.
You're welcome.
Have a good night.
Okay.
Amy.
Bye.
So next week, we've got lesson 6 and 7, and then the following week is our test.
Okay.
So I was trying to remember if there's anything special I want to talk about next time. Oh, technically today begins week. Oh, that's funny that they started that on Thursday. Usually, okay. So they are opening things up a little bit early. So as far as next week, we're going to talk about the Central Limit Theorem and the sampling distribution. So you're definitely going to be using this again. Basically, we're going to be dealing with probability. So you'll definitely be using this all over the place. You can see what's in the tails, what's on the right side, what's only on the left side. So hopefully you get really good at that.
Yeah, I had a little trouble today.
Okay, but you got it now?
Yes, I think I understand it now. I just, I didn't realize they had to be highlighted in a certain area.
Oh, okay. Yeah, that's the thing that always trips up people. And it'll even still trip up people, even though they know that, it'll still trip them up on the test. So just be ready for that. So one of the things that I could do, if you don't, so this week doesn't seem too bad. Do you want me to give you a preview of next week?
Sure.
Okay. So this is kind of a little fun thing that we do with the Central Limit Theorem. So let's say, for example, so just as a preview of the Central Limit Theorem, the Central Limit Theorem basically says that even if your underlying distribution is not normal, the mean of the distribution is often normally distributed. Which is really cool, because what that means is even if our underlying distribution is not normal, a lot of times we can still use the normal distribution when we're looking at sample means. So let me give you a for instance. This is kind of a cool example. So let's say that I'm doing a simulation and I want to find a bunch of random numbers between. Now you don't need to do this. I'm just doing this as a demonstration. Between 75 and 125. Okay. So I'm going to do this 9 times 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. These are just a bunch of random numbers, and then I'm going to go down 100 rows. 100 rows. Okay. So these are literally just a bunch of random numbers. Okay. Now let's pretend. So I'm going to pretend this is a school of 900 students' IQ scores. Okay. And I'm going to say that each row represents a random sample of 9 students. Okay. So we could figure out, I'm going to insert a row here. We could figure out what the population mean was. Population mean. Okay. And in order to do that, I would simply find the mean of all 900 students. Okay. So I'm hoping when I do this mean that it's going to be close to 100, and we're going to see what happens. 100.356, that worked out pretty well. Okay? Now, if I were to take, the problem is, I should save one of these things here, but I'm just going to take one row of this, or one column. If I were to take this column of 100 students, okay, I'm going to stick it in the Histogram Maker sheet, which is in the, is it this one? I hope it is. It is. No, it's not. Oh, it is. Histogram Maker. And so as we look at this, so this is a Histogram Maker. This is only 100 students, but the other rows should look the same, other columns. So would you say that that looks like a normal distribution to you?
Yes.
a bell curve?
No.
No, it doesn't. And in fact, if these were random numbers, you would expect these to be just random all. So this is actually what we would call a uniform distribution. It should look basically like a rectangle, and it basically looks like a rectangle, okay? So you can see here, and if I did this for all 900, I only did it for 100, but if I did it for all 900, it should look like a rectangle, because these literally are just a bunch of random numbers. They should be evenly distributed between 75 and 125, and it appears that they are. So this distribution is not normal. Would you agree with that? Not normal, not a bell curve.
Right.
Okay, it's normal, but it's not a bell curve. So by the way, I should just one little tidbit of information. The guy who discovered the so-called normal distribution, the bell curve, his name was de Gauss, and apparently he had a mathematical rival, and it's called the Gaussian distribution. And this rival didn't want to call it the Gaussian distribution because he didn't want to give this guy any credit. And so he called it the normal distribution, and for some reason that stuck. And so that's why we call it the normal distribution. But technically the name is the Gaussian distribution, after de Gauss. All right, so at any rate, I'm going to erase all this data here for a minute. But you could, well, maybe I'll leave it there for a second. I'll erase it in a minute. Okay, so let's go back to our data set that we had open, which was here. So let's pretend, for example, that I want to find the sample mean of each row, okay? So if I do the mean of the first row, now there's only 9 students in this, okay? So I get a sample of 98. I'm going to do this for all 100 rows. Okay, so I did this for all 100 rows. So you can see I got a 98 and a 106 and a 99 and a 106 and 95. So these, each row, the mean varies, right?
Right.
Okay, so sometimes I get as high as 106, sometimes I'm down as, oh, there's 110. Sometimes I'm down, I don't see any low ones. Oh, 93, that one's 91, these are kind of low. Okay, so these are going to vary. Okay, now what the central limit theorem says, if I were to take just the sample means, so each of these 100 sample means, okay, you saw what happens when I did the first data here.
Right.
I'm going to replace this data with just these sample means, and so my question is, do you think that you will get a bell curve, or will you get another rectangle like we got the first time?
I think we'll get another rectangle.
Okay, and the central limit theorem says you're going to get a bell curve, and so let's see what happens when I paste this data. Look at that. Okay, and so the central limit theorem doesn't apply to raw data like the first time. It applies to the sample means. And so if I take the distribution of the sample means, that is going to form a bell curve, which it did. Okay, now let's do another thing here. Okay, so I'm going to take the mean of my means. Okay, so my question to you is, if I take the mean of all of my means, do you think, oh, what happened here? Do you think that the mean of my means, will that be the same or different than my population mean, which is 100.3656?
I think it will be different.
You think it will be different? Okay, yeah. So we're going to find out here. The mean of my means is exactly the same.
Okay.
Okay. So what's cool about this actually illustrates the central limit theorem. Okay. The central limit theorem basically says if you take the distribution of your sample means, it will always form a bell curve, and not only will it form a bell curve, but the mean of the means will be what we call an unbiased estimator of the population mean. Okay, and you can see that this is exactly the same as that. Okay.
Yeah.
Now, so what that means is, even though, remember our underlying distribution when I did this first 100 data points, if it was just too hard to do all 900, and I knew the 100 would look the same as the 900. But remember, when I went back here the first time, oh, you're gonna make me do all this, okay? I got a nice uniform distribution, a nice rectangle. But then when I pasted my means, it became a bell curve. And so what's fantastic about the central limit theorem is basically it says that when you're worrying about the means, that it will always form a normal distribution, and it will be an unbiased estimator of the population mean if your sample size is large enough. So then the question for students becomes, what's large enough? Okay. So typically the central limit theorem says it often works if your sample has 30 in it or more. Now the interesting thing is, notice each one of these rows, I only did a sample of 9. So sometimes it works for smaller numbers than 30, but 30, so here's the question. So here's one of the things. In fact, I just gave this lecture today in my UVU class. And one of the students missed a question, and basically it came down to, oh, I gotta find this again. He said, well, if your sample size is large enough, can't we assume that it's normally distributed? And I say, you gotta be careful about that. The central limit theorem is not a magic wand where you go, oh, my sample size is 30 and therefore it's automatically normally distributed. Now, back a few years ago, I did this presentation for the math. It was Math Week at Utah Valley University. And so I work for ESPN. Did I tell you guys that yet?
Yeah.
Okay, good. So I hadn't told my UVU class. And so anyway, so this is me sitting next to Corey Williams. I can't remember what the other announcer guy's name was for ESPN. Typically, I don't sit courtside, although I did that game. Typically, I'm in the TV truck. And I'm in here with all these TVs. And so my brother, Ryan, got me hooked up with this. It's a fun job. I've been doing this for about 20 years. I'll probably show you this again later on in the in fact, maybe we'll go over some of this today. But the thing that I just wanted to mention was a few years ago, there was an article that said Patriots don't fumble. And are you a football fan?
My husband is. No, I'm not a big football fan.
You're not a big football fan.
I watch my own kids. But...
Okay, well, I'm a big Patriots fan. And the Patriots are in the Super Bowl. And a few years ago, this is Tom Brady here in the middle. Mm-hmm. And they had a thing where footballs have to be inflated to a certain amount, and Tom Brady was he was accused of underinflating the footballs. And so this guy did this big mathematical article in here and said, basically, he came up with this graph, which I've never seen, and this is the Patriots right here. And he said, look at this. This is the rest of the NFL, and then you've got the Patriots way up here. And they're like, the reason why the Patriots don't fumble the ball is because Tom Brady has been underinflating footballs, and it's not fair. Okay. And so one of his conclusions, he says, what are the odds? And the odds that the Patriots would be that far out of whack would be 1 in 16,000. But he was also assuming that this was a normal distribution. Okay. And of course, so your sample size is a lot bigger than 30. And so some other mathematicians came out here and they said, all right, I'm just going to fly through this really quickly. Well, first of all, so this is the response to the first article that said Patriots are cheating. And so they said, remember, there are some cheaters like Barry Bonds and Lance Armstrong. I'm sure you probably heard of Lance, that were outliers. But Phil Jackson, who used to be the coach of the Bulls and the Lakers, he was an outlier and he wasn't cheating. So, so at any rate, sometimes you can find things because you're looking for them. And one of the things that he said that were flaws in the first argument was they refuted this 1 in 16,000 number and said it was more like 1 in 300, which is still kind of small, but it's a lot smaller than 16,000. And the reason why was because, for one thing, he mixed together some special teams plays and excluded other ones like kickoffs and fumbles. And he also made an assumption that the plays per fumble was normally distributed, and it is not normally distributed, okay? So the thing that I want to point out with the central limit theorem is it is not a magic, it's not a magic wand. Sometimes it works when your sample size is as small as 9 or even smaller. Sometimes it works, but usually, so the number that we like, that you're going to read in the textbook, that you're going to hear a lot, is as long as, in fact, a lot of students here, and this is what I want to be careful about, if your sample size is 30, it's automatically normally distributed because of the central limit theorem. And I want to emphasize there is nothing automatic about this. You still need to go in here and you need to make a histogram or a QQ plot, as we will learn later, especially if you have a small sample size. Have we learned about QQ plots?
Yes, at the end of this lesson,
okay.
They notice a few.
Okay, so if you have a small sample size, like 9, sometimes you can get away with that. But generally, so for example, let's say that I took this data here, and I wanted to find out, is this data normally distributed? Because I've only got a sample size of 9. It's a very small sample. What I could do, I could delete all this. Oops, didn't delete there, that's all right. Now I gotta copy, I want to delete this though. So with your QQ plot, where did it go? What's that? Why can't I pull up my other thing here? There we go. I'm going to paste this here, and the only thing is you need to sort your data, because if you look at it unsorted, well, this definitely doesn't look normally distributed. But if you sort your data, now it roughly follows the red line, okay? So we would say that, yes, even with a small sample size, we could assume that that's normally distributed, okay? So basically, if you can verify with a histogram or with a QQ plot, you can get away with smaller sample sizes. But generally, the central limit theorem works when your sample size is, and by the way, I did 100 here. But once again, it's not a magic wand. It doesn't always work, but it works most of the time, especially with means, okay? You just have to verify that in this case, the histogram looks like a bell curve. Does that make sense?
Yes.
Okay. So hopefully every semester people think that 30 is this magic number. It's not magic, especially because you're going to need to know this information for your final project. And that's one of the biggest mistakes on the final project is people say, oh, our sample size is 30, therefore it is automatically normally distributed. No, there's no therefore. You need to verify if your data look normal. And by the way, I will say this, especially if you're doing a matched pairs project, well, you're comparing prices between Walmart and Target, or Walmart and Kroger, or whoever, Amazon and BYU bookstore, or whatever. A lot of times that data is not normal. So you look at your histogram and it's not normal. Okay, so 30 is not magic. Okay. All right, so here's the other thing that I wanted to mention here. So the central limit theorem says that even if your data is not normal, the sampling distribution is normal. Now, we can also find the standard deviation for the population. Okay, and so this is going to be the standard deviation for the population, and I'm going to do this for all 900 things here, and that gives me 14.5, which is about close to 15. Okay, Now, the other thing that I want to do is I want to find the standard deviation of my samples. So when I do my standard deviation here, okay, I'm going to back up here, and I'm going to ask you a similar question I asked before. When I press enter, do you think that my standard deviation of my samples is going to be the same or different than the standard deviation of my population?
I think it's going to be the same.
Okay.
I've said the wrong thing every time. So
And it's different. So you got your answers backwards. Okay. Now, a lot of times what happens is, especially when we're doing a probability next week, they're going to give you, here, I'm going to do it this way. There is a relationship between those two variables, and I'll tell you what they are in a minute. If I do the Z-score formula, and this is the one I want here. Okay, they're going to give you this formula here, Z equals X minus mu over sigma. And then you're going to see a very similar formula. I think this is going to be lesson 6, and then in lesson 7, they're going to give you this formula, which looks very similar. Z equals X bar minus mu over sigma over the square root of n. Okay? And so people are going to be like, do I use this one or do I use this one? Here's how I'm going to answer that. Okay? I'm going to say use this one all the time, even if the book tells you to use this one, and here's why. Okay? You'll notice here, basically, the main difference here is one is divided by the square root of n and one is not. Otherwise, they look extremely similar. So here's what I'm going to say. This is the better one to use, okay? In your problem, because a lot of students like to confuse these two formulas, okay? In your problem, if an n is given to you, use it. So if it says your sample size is 36 or 42 or whatever the number is, this is the formula that you're going to use.
Okay.
If your question does not have a sample size, it just says you want to find, whatever percentile or whatever, you can still use this equation, okay? And if there's no n, assume that n equals 1, okay? Because if n equals 1, then this equation becomes this equation, okay? Because you're dividing by the square root of 1, so it's exactly the same. Okay, so if you just want to remember this formula here, just remember my rule. If there's an n, use it, and if there's not, assume that n is 1, and then it becomes this equation, and then they're basically exactly the same. Okay. Now, technically, they're not exactly the same because this says x, and this says x bar, which means I'm using a sample mean. But a lot of times, I just tell people this is the data minus the mean over the standard deviation over the square root of the n. And this is the data minus the mean over the standard deviation. Okay, but they're so darn similar. I know students mess them up, and I just say use this one all the time, and just remember the rule about the n. If there's an n, use it, and if there's not, assume that it's 1. Does that make sense?
It does. It's
okay.
Good to know.
So that's your preview of next week.
Okay.
Okay.
All right.
All right. So, do you have any other questions for me? Oh, actually, one more thing. In fact, it relates back to what this was. Okay. So you notice one's divided by sigma, one's divided by sigma over the square root of n. Okay. Now, the fact of the matter is the Central Limit Theorem says there is a relationship between this and that. And what it says is you can estimate this standard deviation very easily if you take the population standard deviation and you divide it by the square root of n. Now, since each row is 9 students, I'm going to put a 9 here. My sample size is 9. Okay? And so if I take by population standard deviation and if I divide by the square root of 9, I'm going to get an answer that's very close to 4.79, 4.84. See how close that was? Okay, so that's kind of the relationship between these two things here. If you take and divide your square root, your population standard deviation divided by the square root of your sample size, you'll get a very similar answer here. So it's a good estimator. So, and in fact, that's why we divide by the square root of n, because then this becomes an unbiased estimator of the standard deviation. Okay?
Okay.
Because now these are very close. When you compare this and this, 4.79 versus this, it's a biased, this is a biased estimator. But now when I divide it, it's unbiased. It's very close. In fact, the cool thing about the central limit theorem, not only are these close, the population means, they're exactly the same.
Right.
Okay? This is how you get an unbiased estimator. Does that make sense?
By using that formula?
By using that formula. And so that's why in this formula, we divide it by the square root of n, because it makes the denominator is now an unbiased estimator for the standard deviation of the mean.
Okay.
Okay?
Right.
And so these two equations are related. And so when you're using samples, you use this one. When you don't need samples, when you're just using data, this one works. But anyway.
Okay.
Okay?
All right. Thank you.
All righty. Do you have any other questions for me?
No, not today.
Okay.
I'm sure I'll have more later.
Yes. Well, I'm glad nobody showed up on Monday, so there was no video. But so we're going to meet every Monday and Thursday, and I'll try not to be late.
Okay.
The question was, do I leave and go home, or do I? And I was like, oh, nobody came last time. We'll see. Anyway, so of course I was late today, and you guys were on time, but nobody came last time, and I was like, I don't know what to think about this class.
I'm
So,
sorry.
do you think you'll be here Monday?
I'm not sure. I work 2 days a week.
Okay.
And I work next Monday, so
Okay, no problem.
so I won't be, but I might be.
Oh, you
again
won't
on
be.
Thursday.
Okay.
Yeah, I
Well,
have to work. So
hopefully other people will be there. That's fine.
great. I might
Alrighty.
stay 15 minutes. If we don't show up in 15 minutes, you could go home.
Oh, by the way, this is our TA, Adam, for section
Adam.
7. Are you in section 7, Kim? Do you know? Or are you in section 10?
I have no idea.
Yeah, I don't know either.
What I know.
So he might be your TA. So Adam's our TA for section 7,
It says
and
10.
Kristen is section 10. So
I'm 10. I'm in
you're 10?
10.
So
Mhm.
okay, so Kristen will be your TA. So
Okay.
so Adam's great to help out, and I always like to talk to him after our meeting ends. So this is awesome that he's here. So
Yeah, am I a little too early?
no, you're fine. This is perfect. Okay. So
I'm gonna go then. Okay.
all right, so we're gonna end our office hour that I'm gonna post, and hopefully it will, when I get done talking to Adam, we'll actually have a video to post in the announcements. So
Okay. All right. Thanks for your help.
you're welcome. We'll see you later.